I hope you can see this. Just give me confirmation.
Yes, yes,
Okay, thank you.
yes.
Great. So today is about modeling and experiments or measurement techniques, and they go hand in hand. So it's I think it's good to plan them in the same day or one lecture after each other, because one of my main claims here is that they are very much related, and experiments are become better when you combine them with models, and models become better when you combine them with experiments also. So it's good to bring these two together. I have tried to separate modeling and experiments into two different lectures, but again, you will see a lot of connections. I think it's one important question then that you always try to combine and to learn from both to make one support the other and vice versa. So I will start. This lecture is maybe a bit different than the classical one. I will try to make it a bit more dynamic and entertaining. And I will start with some claims that we will be back after this lecture and we'll revisit these claims. But first I will just announce them. And it's three claims. One is in modeling, within modeling. There is this claim from George Box. He was an American statistician. And he said that all models are wrong, but some are useful. And I think this is an extremely wise sentence. Short, it's only 7 words, but they tell a lot, I think. Meaning that no model is perfect. There will always be imperfections. There will always be some assumptions and some simplification of reality. Whether you're doing DNS, the most advanced and resolved CFD, there will still be imperfections there and assumptions. But the thing with modeling is that some of them are useful, and that is the whole meaning with modeling. That's the question we need to ask ourselves. What is modeling for? Why am I doing this? What is the meaning? What is the use of this model work that I'm doing? And I think one always should try to ask oneself, is this useful? Is this going to be useful? Why am I doing this? This is wrong in some way, to some extent. It can be extremely wrong and just a little bit wrong, but it will always be wrong to some extent. The point is, will it be useful? So I think that is a wise sentence, and I will try to revisit it in the end of the lecture. So this was for modeling. For research in general, one claim, which I cannot just assign it to one person, but it's a general belief or truth. I think it's relatively widespread, not enough widespread if you ask me, but relatively, is that theorists and experimentalists do not date each other enough. They should be meeting more. You see people in academia, in conferences, that are pure modelers or pure experimentalists. And I think it's interesting that these people exist, of course. But I think my experience is always that when I meet people that do a bit of both, that do not devote themselves only to one of these, then you win a lot. There is a lot of synergy. So if you are a pure experimentalist, try to learn a bit more of the experiments, and if you are a pure experimentalist, try to learn a bit more of modeling. And I will try to tackle this question a bit more in depth later in the lecture. Why is this important? How can they help each other? So this was for research. We have one claim in modeling, one claim in research, and I have one claim in life, and that's my own claim. And I say that if you have one problem and you want to solve it, you better make it everybody's problem. If it's everybody's problem, you will have more people interested in solving it, and probably you will approach the solution faster. There will be more momentum and interest in approaching that solution. So with this, what I mean applied to this lecture is that, for example, we have different phenomena in fluid ice bed, which is, for example, let's say relevant to fluid ice bed combustion, like the fuel mixing. That is a large research topic for fluidized bed combustion. The thing is that if you make people that are doing fluidized bed gasification, that are doing chemical looping, that are doing pyrolysis, a lot of different processes, if you make them realize that this is also their problem and that solving this or researching this will also benefit them, then you gain momentum by that, a lot of momentum. So I think it's important to, of course, try to solve and to design your application or your process, but try to identify what is the general question in fluidized bed technology, not in the concrete application you are studying, but in the technology itself in general. What is the question which is common also to other applications that you want to solve? Because then you can find partners that are doing a completely different process, in some sense, a different application, but that share the same question with you. And then that will, of course, help you a lot. Okay, so having said this, I will, as I said, revisit this by the end of the lecture. I will just present the index for the lecture today. So first is why modeling? Why are we doing this? Again, it's modeling should have a meaning, should have a use. So I will try to reflect a bit on that. What is the meaning with modeling? And then the main core of this lecture is the different types of modeling, introducing you to the different types of fluidized bed modeling in this case. And finally, how we combine, or how I think one should combine modeling and experimental work. And this applies not only for fluidization, which is the focus in this course, but I think it's rather a general reflection. And this is my view, of course. This has not to be a universal truth, but I would like to share my view on it. So let's start with why modeling then. And I will start with a short story, if you allow. And I have 2 children, and when the elder one was in the kindergarten, then they had a visit one day to the fireman station, and that was very exciting, of course, because one of the fathers of the children in that class was a fireman. So he arranged so that they could visit the station, and that was extremely exciting. You can imagine with everything that firemen use, and all those trucks and lifts, and a lot of exciting things. So he was very excited when he came home after that, and he was very exciting about having this kind of profession that you could work with such exciting things as an adult. And that was the first time he asked me then, okay, what do you work with? What do you do at work? And of course, I felt a lot of pressure. I had to try to match at least, or to come up to the same level as this fireman. So I didn't want to say, well, I'm sitting in front of a computer every day and putting some equations in it. So I tried to picture it in a more exciting way. So I told my child that I was a future teller, a fate teller. And then he, of course, looked at me very surprised, and I said, "Yeah, well, this is what I do. I have my crystal ball in my office, and it's not a crystal ball like a classical you would imagine. Indeed, it is a computer. But what I do with that crystal ball is that I introduce like geometries of a certain unit. I introduce the properties of a certain fuel, and then operational conditions, and so on. And with this crystal ball that I have built, then it will tell me what will happen in future here if I combine all these things. And then it will tell me in this monster of several hundreds of cubic meters how temperatures will look like, how concentrations, mass fluxes, heat fluxes will look like. And he thought this was exciting, and then I was happy with myself that I managed through this situation in a way. But as I say, it's not a crystal ball like the classical one. It rather looks like this. So this is the meaning of modeling, the classical meaning of modeling, to have some inputs which are typically, or should typically, be known and adjustable. So these are things that you can decide on in reality. A model with an input which you cannot act on is not the most useful one, of course. The best model should be that one where the set of inputs consists only of adjustable parameters that you have the power to control. And what is this used for then? Well, it can be used for design of new processes. Now this course is about fluidized bed combustion, and that's a relatively major technology now, but there might be new processes. There are new processes, fluidized bed processes coming on around the corner, and how would those units look like? You need to design them, you need to test them, and modeling is a way to do that. You can do it through experiments, but then this would be very costly, of course, if you just do it by trial and error through different reactors. Then you have upscaling. So once you have your pilot plan, for example, or your bench scale unit, you need to upscale them to the next level. For that, you also use modeling. So once you have a design and you want to scale up the process, you use modeling for that. And then for the most major technologies, then you have optimization. So for example, large CFB boilers, that is a major technology. And what you do with modeling, the meaning with modeling there is to optimize the operation of those units. What will happen if I change the fuel from this to this one? What will happen if I, for example, introduce a heat extraction surface somewhere, and so on. So I see these three classical meanings with modeling: design, upscale, and optimization, depending on the major of the readiness level of the technology, of the process you're looking at. And this is the classical approach, but there are other ways to apply modeling. For example, is to identify key parameters. Once you have a model, then you see which with a sensitivity analysis, you have this crystal ball, and then you change your inputs and see which are the critical ones, which are affecting your outputs the most. For example, you can identify knowledge gaps. So within your model, the different expressions that you use, which are the critical ones, which are the core ones, really making an impact on the result, and are they good enough or not? Where shall we put our research efforts? Where shall we put our experimental work efforts? What shall we investigate? Well, how shall we prioritize our experimental investigations? So modeling is a way to answer that, to try to identify these key knowledge gaps. And finally, also, for example, validate or discard assumptions. Typically, you do some assumptions, but then through modeling, you can typically discard some of them, for example. These are some examples of in the field of CO2 reduction, of how different technologies use modeling. So, for example, you have air combustion, and that's it's a major technology, so you need simply to optimize it. And then you have scale up of, for example, oxy-fuel combustion, calcium looping, chemical looping, for example. So yeah, this is only table with how modeling is being used in different technologies. So this was a very short introduction on the meanings with modeling. I think it's also always a good question to ask yourself, why am I doing this? If you're doing modeling, what is the meaning of that? And out of that, be consistent with your choice of inputs, outputs, and so on. And also to be consistent with the type of modeling that you choose. I mean, this crystal ball can look very different depending on what you want to do. And I will give you a bit of a historical perspective of how modeling, or how these crystal balls have developed in the field of fluidization or fluidized bed combustion. We start with industry, and what historically industry has been doing is to use experimental correlations. And many of you wouldn't call this modeling, but it depends on the definition of modeling. If we define modeling as this crystal ball that you give me some outputs and the model will give you some, you give me some inputs and the model will give you some outputs, then the use of experimental correlations can, in a way, be seen as modeling. So typically what the industry has been doing is operating plants, and then, for example, they operate in a certain way and they measure CO emissions, for example. Okay, this is an output, and they at the same time monitor during operation what is the air to fuel ratio, lambda, so the excess air ratio. So these are two things that you can monitor typically online, and you can log this data. And out of this, for this unit, then you can have a lot of statistics, and typically one will correlate with each other. I have 3 data points here, and then I try to do, correlate the CO emissions with lambda, and I will find some correlations here. Here I just put some easy correlation, like the concentration CO goes with the power of -1 of lambda, and C0 is a constant. So this is just a simple example of how it could look like. Can be a polynomial with different terms and so on. So this is, in a way, or not in a way, but this is very much like how industry has been doing. Now this is very primitive, probably, but it works, of course. The problem comes when boiler manufacturers say, okay, then we are building a new boiler, and we have data from this boiler, which gives us this curve. Then we build a new boiler and we design it, but it will have a different height. What happens then? Shall we trust this curve or not? Well, historically, what the industry has been doing is to say, okay, we just build it a bit higher and still use the same curve and hope that it will not change that much. And when they have built the new boiler, then they log data on the new boiler and they can expand their correlation. Now it's two-dimensional. They have the 2 boilers, so they have the lambda CO relationship for 2 different boilers, one with this height and one with this height. So you have 2 curves. And suddenly now you have a correlation of CO emissions based on 2 different inputs then. And well, as you can imagine, this becomes, this is just the beginning, so to say. This is a never-ending story. Because then, okay, what happens if I change my mass flow of fuel? That adds another variable. Then it will be a the correlation will depend on 3 different inputs, not only on 2. And not only the mass flow of fuel, you have the width, the cross section of this boiler, for example. You have the injection of secondary air, how much you're injecting, at which height you're injecting, and you see, you end up with a lot of variables. You have the temperature level, you end up with a lot of variables, and that is one of the main drawbacks, so to say, that things become more and more complex as more and more inputs come into the picture. So I call this approach is one end of the scale, one extreme way just to believe on measurements, so to say, and empirical correlations. But this is very much how boilers have been designed and developed for the last 30, 40 years. And I call it the empire of proofs, purely empirically based. And there are enormous data banks in the boiler manufacturing industry, really enormous, with a lot of data. The drawbacks with the empire of proofs is that you are uncertain in extrapolations. What do I mean with that? Well, if you have for example, this case, we had a boiler with this height and we have a boiler with this height. Yeah, I would be rather confident that if I have a boiler with a height in the middle of these 2, this correlation would work rather nice. But I wouldn't bet my savings on that this correlation will work fine if we extrapolate a lot. If we have a new boiler with a height much lower or much higher, or so far away from the data domain that we have. And this is typical for upscaling then. If you want to grow bigger, you have never done it before, that is extrapolation of your data. And how sure can you be of that? And as I said, that this approach becomes less useful as the number of input increases then. Characteristics for this is that, well, typically these models are black box, are 0-dimensional. You have a set of inputs and a set of outputs, these correlations. They are steady state typically. And if you put it into a computer, the computational effort for this, or the time scale for that, is less than seconds. I mean, this is very, very fast. It's milliseconds, I would say, or microseconds even. And that's the main advantage, of course. Okay, this is one end. This is one extreme. What do we have on the other end? Well, we have modeling in academia, and that is based on theoretical expressions. And I call this the kingdom of equations instead. So not a lot of probes and measurements from large-scale units, but rather a lot of equations. And as I said, this is an extreme case. Of course, there is academia, and luckily doing a lot of experiments, and that's good. But I'm just showing here what is the extreme case. And if we look a bit more into this kingdom of equations, give me 1 second, please. One first thing to present, which is important, is in terms of modeling for fluidization, is this continuum against discrete elements. So this is a very interesting experiment. I mean, when you see this, these are birds flying together, and well, they create these very nice shapes which move in very exciting ways. I love to watch this in the night skies in Sweden. Yeah. So for sure you have seen these scenes before. So when you show this to yourself, or when you look at the sky together with someone at this, it's fun to see that some people, depending on how their brain is built, some people see a lot of birds, and these people think in terms of discrete elements, while some people do not see those individual birds a lot, many birds. What they see is a kind of continuum, the whole group, so to say. They see it as a group. And it's exciting. And well, you see these two guys. These are to the left, you have Euler, and to the right, you have Lagrange. And these are two scientists. And one was very much minded into the continuum thinking, the other one into the discrete thinking. And what is the difference here? Well, if we take here a domain in this picture, with a certain characteristic length, so the side length of this domain, and we gradually reduce it, how will the bird concentration look like in a figure as a function of this characteristic length? Well, it would look like this. For very large lengths, we will have that the average concentration, average over the whole domain, is relatively constant, but at some point when the domain is small enough, we will start seeing fluctuations, because when one bird disappears from the domain, it is important enough, or the total amount of birds of the domain is small enough so that that bird makes a difference. And then we would see this kind of fluctuation. And eventually, of course, this curve goes to 1 if it meets a bird, so to say, when it's a differential length, or if it doesn't meet a bird, it goes to 0 then. So this is the definition of what is a continuum and what is not a continuum. So if you are in this region, if your cell size is in this region, then you can approach the whole thing as a continuum. You can define what is here inside with some continuum properties in terms, for example, of density. And this is what you typically do, for example, with the ideal law of gases. What you do there is that you have a lot of gas molecules, but since you're not studying the molecule scale, but much larger scales, then you define things such as pressure or viscosity. And these are things that they do not exist at molecular scale. But when you go up in scale and you start averaging properties, then these continuum properties appear, and pressure and viscosity are examples of this. Well, in the same way that you do this for gas molecules and for the continuum, so to say, when you, instead of looking at the discrete molecules, look at the gas as a continuum for the larger length scales that you define these properties. The very same thing you can do for solids and solid suspensions, which you have in fluidization. So if you look at large enough length scales, you can also define viscosity for that media, this mixture of gas and solids. You can also define even pressures or temperatures and so on. So depending on how they fluctuate and so on, you can define properties similarly as in the same way that you would do for a gas. Okay, why this? Well, again, on the discrete scale of each of these elements of each of these particles, we would have Lagrange. If you would like to think in terms of a continuum, then you would have Euler, and that is how the modeling in the kingdom of equations is called. There are two types of modeling mainly. One is the Lagrangian approach, and what you do there is that you model your solids as Lagrangian, as individual particles, each of them, and your gas typically as an Eulerian phase. So you don't account for each molecule of your gas, you see the gas as a continuum, but you see your particulate phase as individual discrete elements. And then this is called the Lagrangian Eulerian modeling. And what you do then, of course, is to solve the equation of motion for each of these particles. And you can imagine that this is affordable for a certain number of particles, but as the number of particles increases, then the computational cost of this increases exponentially. So it becomes very, very costly, and typically you could afford these calculations for 2D domains or for very small 3D domains, but this is not realistic for units, lab units, or definitely is out of reach for large scale commercial units. You have far too many particles to be able to afford this computational cost. In order to tackle this, then what you have is the approach of seeing the particulate phase as a continuum, and then this is called the Eulerian approach. And then you define equations for the particulate phase the very same way you would define them for solids. So with a viscosity and with a certain voidage and pressure and so on. So these are the main two families, so to say, when it comes to modeling in the kingdom of equations, as I call it, or CFD, as you may know. Well, so these are, as I said, Eulerian, Lagrangian, Eulerian. There is a third member of the family that is somewhere in the middle, and this is CPFD, Saline particle fluid dynamics, and that is some kind of compromise in the formulation for the particulate phase. It's somewhere in the middle between Eulerian and Lagrangian, so it wants to save time, but it still be a bit more academic, so to say, in the formulation of the motion of the particulate phase. And that is the code for that, or the software package for that has become popular in the last years, is called Barracuda. You may have heard about this. But it's a compromise in between the two, so to say, as a short summary. Well, what are the characteristics of this? Much different than what we had in the kingdom of proofs. What we have here is typically length scales for your cells, so to say, or the length scale of your modeling. Some decimeter at least, but this is very large for CFD. It should be typically here in the order of millimeters, micrometers, or just below some millimeters for your cells. And then, of course, you can go to micrometer scale if you want to be very, very resolved. In the end, you could have DNS modeling, direct number simulation, which is the most resolved you can have. So this is for the length scale. The time scale for this is typically in the order of milliseconds is typical, but I have seen simulations in the order of seconds. But yeah, you have also time resolutions in the order of microseconds also. So this is the time step for your simulations. And well, how much time does this require then to simulate a boiler, a large-scale boiler? Well, a large-scale boiler would take months, Eulerian simulations. It would take decades if you were doing or daring to do this Lagrangian Eulerian simulations, but no one has, of course. So we have this Eulerian. What are the basics there? As I said, it's transport equation, so you treat the particulate phase in the very same way as you treat the gas phase. And most of you probably know this, but I just want to make a recap here. So the transport of in any quantity, heat, momentum, mass, the transport equation for any of these magnitudes can be expressed as a variation, which equals the variation will equal the incoming minus outgoing, so the net transport in and out from a domain. And then you have also a source term, and the source term consists of the generated mass, momentum, or heat in that domain minus the dissipated one. So the variation will be the net transport plus the net source term, the net generation. So indeed, you have this. I always put the example of a room, for example, or a house, a flat. So if you ask the question, how many people will be here in 1 year, that will be the variation of number of people in that house in 1 year. So this is a derivative with time, a variation with time, will be this, the transport term. So in total, during that coming year, how many people will have left the house and how many people will have entered the house, plus the source term, how many people will have been generated in that house if there are newborns, and how many people will have be dissipated, will have died in that house. That would be a source term. It's not a transport, but you are modifying the mass balance through generation or dissipation within your domain. So yeah, instead of people and a house, you can define, for example, mass and a computational cell, so to say, and you make this balance for all these computational cells, and then they would look like this. This is, as I said, variation with time. If we're making a balance on a random arbitrary magnitude here, it can be heat, it can be momentum, it can be mass, anything. So this is just a pure balance. You cannot say it's false. It will always hold true that the variation with time will be the transport in and out. And there are two terms for this transport. One is the convective term, how the velocity will bring in and take out from the domain this property that we are balancing, and also diffusional or dispersive transport term. So there is convection and diffusion in this transport. It can occur in two different ways. And then we have, as I say, the sum of of the source terms. So now if instead of formulating this for an arbitrary value, we formulate it for the mass, for the energy, and for the momentum in fluidized beds, we would have this. For the gas species, you have the two balances, and you see the terms that I presented just above, and this is how they look like. So here you're making a balance on the species, a certain species which has this concentration. It's a gas species I, and then you have a solid fraction or species J, and then you make one of these balances, mass balances, for each of the solid fractions or solid size intervals, and also one for each gas species. And you make this in every computational cell and for every species then. For the energy, what is typically done is that to take the assumption that both phases hold the same temperature, and this is something that you can prove or shortly calculate, that particles are typically small enough and the heat transfer is high enough to ensure that they are in thermal balance with the gas surrounding them. So if you assume that both phases are in the same, holding the same temperature, then the change in energy, in heat, which is expressed as a sensible heat here, the change in heat in a certain cell will be, again, the convective transport of heat, the conductive transport of heat or dispersive transport of heat, and then different source terms, which can be chemical reactions, which can be then convection or radiation to heat exchangers. And finally, we have the momentum, and we have the momentum for the gas phase and for the solids fraction here. And how momentum changes with time for both will be, again, a convective term, and then a diffusional term, and then you will have some source terms. And of course, here comes the big difficulty with Eulerian modeling. For the gas phase, we have this viscosities, for example, and we can define a pressure for the gas phase. And this is very well known from single phase modeling of gas reactors. So you have quite a major modeling field and quite a good knowledge of how this looks like for the gas phase then, in terms of viscosity and so on. The problem is with solids fraction, then we need also to define a certain viscosity of the solids. And how do you define that? How do you model that? Then you need, in each turn, you need equations and models for that. So this becomes very complex. And nonetheless, we have a difficulty on how the two phases exchange momentum with each other. So the gas and the solids will exchange momentum. This term is the same, but just inverted in sign, because the total momentum has to be conserved. But this exchange coefficient of the momentum, how does it look like? It's another of the big questions. So this last equation here, this is the one that makes it difficult or uncertain still, that these results, the CFD of multiphase flow, is still suffering from some uncertainty. It's not fully mature yet because of these uncertainties in some of the terms here. So typically what you would do is that you solve, I have highlighted here the variables that you solve for, the unknowns. And here I made a balance of how many equations you have, how many unknowns you have. And as you see, they match each other, so to say. So it's a determined system. Well, what I said is that these momentum equations, they are troublesome. We are not, they're not mature enough. So what some people do is to disregard them. And of course, life would be very easy if you just have a problem and you disregard it and now problem solved. What is the problem with disregarding these equations? Well, you still have the same variables to solve here. All these velocities, you still have to solve them, but now you have less equations. You have removed these momentum balances. So you have a system which is underdetermined, and then you cannot solve the system. It cannot be closed. So how do you do? Well, you have the same unknowns, but you lose equations. Well, what you need then is to find other equations, other ways to formulate these unknowns, these velocities that you cannot solve through the momentum balances. And this is typically what you do in so-called semi-empirical modeling. You disregard the momentum balances and you find other ways to model or to describe, to approach the velocities. Here we have, for example, one thing that we use in our model is to use this equation for the gas velocity. So we use a potential flow equation. It's very simple and it takes almost no time to solve, very low computational cost. And then you have this definition of the velocity. And then, for example, it gives you this velocity fields for a CFB boiler. So this is one way. You make an approach and then you make the assumption that the gas can be approached in this way. And then you can determine your system of equations and solve it again. So what happens then is that we move a bit more to the middle. We don't solve the momentum balances. This is something you do in here to the right. If we move to the left and drop the momentum balances, we don't solve them anymore. We only solve the mass and energy balances. Then we are doing something different. We are not doing CFD. I would claim that the difference, the border for CFD is here. When you drop the momentum balances, then you're not doing CFD anymore. Computational fluid dynamics, the movement of the fluid, that is given by the momentum equations by solving them. If you remove them, then you're not doing CFD. You are still solving 3D, 500,000 cells, these mass and energy balances. They will give you colorful plots and so on, but it's not CFD, it's something else. I call it semi-empirical modeling. Many people call it semi-empirical modeling. And in this scale between the kingdom of equations and the realm of proofs, I call it the land of all, so to say. And here in European culture, this represents justice. This represents a balance. So in our culture, this represents that this balance that this woman is holding represents that the crime that you have committed and the punishment that you get should be in balance. There should be a justice here. And why I'm using this is because here in the middle we are trying to get some balance between the equations you use and the experimental data you use. You do not only use probes and experimental data, you do not only use equations, but you try to balance the use of both. And for example, we balance the use of both here when performing this. Then we go and try to measure gas velocity in different places and try to validate this assumption. So this is an hypothesis formulated, and then you validate it or discard it through measurements. In the same way, you can do measurements, and measurements can help you in formulating new hypotheses, so to say. So you can have expressions, modeling expressions, which are based on experimental observations. And this is what I mean then by the combination, the synergy of experiments and equations. If we put numbers, then we would have typical lengths are in the order of decimeters of these cells. You can do transient, but typically what you solve is a steady state, and it would take some hours on a desktop computer. We have a model for this for large-scale CFB boilers, which we have developed with the boiler manufacturing industry, and it typically takes about 5 to 6 hours to solve. It's about 500,000 cells, but with efficient solvers and so on, you can get it solved in some hours. And again, it does not contain momentum balances. It contains assumptions on what are the velocities of the gas and the velocities of the solids then. Okay, so this would be then the whole picture. If we look a bit more into this region here in the middle, the land of walls, semi-empirical modeling, as I call it. So you have CFD modeling to the right, you have empirical correlations to the left, and then semi-empirical modeling somewhere in the middle. And this is a gray scale, of course, where you are. It's hard sometimes to put a boundary between the three of them. But if we look into semi-empirical modeling, an historical perspective is that there have been some models for large-scale CFB combustion. The pioneer here was the International Energy Agency. So people from academia, from different universities all around the world that made a common effort, and there was a PhD student that everybody was helping to put together a model. This was a 1.5 or 1D dimensional model. And this was the pioneer. More or less at the same time, we had these models in Germany, the Hamburg University, and it has generated a lot of PhD theses. They had an industrial partner, a boiler operator, and then we had in Finland, fostered by Foster Wheeler, we had also a model developed by Lappeenranta University, and there is a PhD thesis on that. And also here at Chalmers, together with another boiler manufacturer, Valmet in this case, we have also developed a model. So these three models after the International Energy Agency are three-dimensional then. And this is just an example of what our model gives, for example, in terms of heat flux to the wall. So this is the heat extraction, how it changes depending on where you are in your furnace walls, in your water walls. Well, this is the cell discretization of a typical boiler, more or less, how it looks like. The red points are the fuel feeding points, blue points are secondary air injections, and so on. And I think a figure that summarizes very nice is given by Mio Hänen, and this is the author behind the development of this Finnish model with Foster Wheeler. And I think he put it very nice here. So rather than a competitor, he's a good friend and a good colleague, and I admire this figure a lot. I think it gives clarity. It tells us about the space scale and the time scale in both axes, and it maps the different modeling approaches that we have. So in the very large scale with no spatial resolution, 0-dimensional, then we have steady state and 0-dimensional length scale. We have this correlation, these empirical correlations in this region. And then you see that there is some correlation in diagonal. You don't have anything here in the extremes with a very large time scale and very discrete space scale, or the opposite here on the other end. There is a diagonal here, and it makes sense. The more resolved you become on the spatial scale, the more resolved you become also on the time scale. So as I say, this is the semi-empirical models, and they can be 1D, 1.5, 3D, and this is what I have been mostly working with, this kind of modeling. And this is a macro scale, and typically you would do steady state, but you can also do transient modeling. We have been doing this transient modeling 1.5D also. So we have a 3D steady state and a transient 1.5D model. And then here you enter the field of CFD then. And then you have CFD Eulerian here. Then you have CFD Lagrangian Eulerian. It's a bit more resolved on the time and space scale. And finally, you have the most resolved ones, which are DNS, direct number simulation. So I think this gives a good picture, a good representation of the different types of modeling that you have. And maybe something that was lacking here, maybe it's too obvious, but I still would like to highlight it, is the need for empirical input. In this very extreme in DNS, you hardly need any empirical input. You can do this without touching a probe or getting your hands dirty. But here it's the opposite. Everything will be based in principle on empirical input. And then you have a grayscale, a gradual increase in the need for empirical input in this direction. Well, and finally, I would like to end with some reflections on the combination of modeling and experimental work. And if you allow, I will just take care of my throat for a second. Yes. So some empirical modeling, as I said, then you drop the momentum equations, which are not mature enough, or there are terms in them that put uncertainty in the results, in the validity of the formulation of your model. And then you're left with mass and energy balances. And if you do this and you do some mapping of what are the unknowns here, well, then you have velocities are unknowns because you don't have the momentum equations. So then you cannot solve velocities. So they are suddenly unknowns. And as I said, you need to find formulations, model descriptions, assumptions for these velocity fields. That's one. But there are also other things that you need in this kind of modeling. There are this mixing. What is the dispersive mixing of this? And if you remember in the lecture last week about solid and gas mixing, I gave you some material on this, on how to, which efforts have been made to evaluate these coefficients and to study them, to analyze what they depend on, and so on. So that is why there is a lot of work on these coefficients, because you need them in these equations for these models. So here we see them again, our old friends from last week. And finally, then we have different source terms. Then and this would be the kinetics of the gas reactions, the heterogeneous reactions, and here the kinetics. The kinetics of the homogeneous reactions for the gas phase, and here for the heterogeneous reactions, of course. And the same goes then. I mean, the kinetics will have some heat of reaction related to them, and this will create a heat release or a heat sink based on that. So all these are kinetics, these light blue terms. And finally, you have the red terms, which are the heat transfer. This is also something to be studied. What are the heat transfer coefficient to the water walls, to the heat exchanging surfaces? So these are things that need to be studied, that in DNS, that in the very resolved CFD calculations, you would get by definition, so to say, solved by nature laws. But when you do this kind of modeling, you need expressions for this. What is my heat transfer coefficient here? Well, and here I have made a list what is wanted when you do this kind of modeling. Well, you need them, the velocity fields, dispersion coefficients, kinetic rates, heat transfer coefficients. These are the things that are needed when doing this kind of modeling. Okay, then how do we do in practice? Well, you need experiments, you need to determine these things from reality, or you need to have some knowledge. You do targeted experiments. You do experiments to try to determine, to evaluate, to understand one of these things, specific things. You don't do global experiments, so to say, to understand everything, but you make dedicated campaigns to try to understand one of these things. And these are called targeted experiments or dedicated experiments. And based on that, you formulate an hypothesis, a model, a description. And once you have that, you test it and you make new experiments to mature it a bit more. So you have here an iteration on how you develop your model, how you mature it and make it better, improve it, and so on. So this is one cycle. Once you have improved your model, your description of any of these variables here, so we're speaking about one of these variables. Once you have done this, you have a new submodel, a new description for one of these variables, this highlighted in color. And what do you do with that? Well, you put it into these equations and you make model simulations. You make a simulation, you solve all these balances and you make simulations of the whole process. So you make these model simulations, you go to large scale data experiments and you validate if your whole model has become better or not. For example, you have made experiments to try to determine better what is the gas dispersion coefficient. You have here this iteration, you mature your formulation. Once you're happy with it, you go and solve the whole thing with your new model for this dispersion coefficient and see what it gives once you have updated this new model, this new term in your formulation, and see what it gives against large scale experiments. So these are not dedicated experiments, these are experiments in large boilers or log data from large boilers. And from this, then you have another cycle on another level between modeling and experiments. Then you make a validation here. Does it work? Doesn't it work? And what you learn from it, you go back, you identify what is the problem. If there is some problem, what is the new knowledge gap? Well, yes, it seems to work, but now this has shown up a problem that maybe we don't know enough about, I don't know, whatever, these kinetics, for example. And these seem to affect the results a lot, and it seems like we don't have enough knowledge. Well, then you have used your model in combination with experiments to identify what is the key knowledge gap, something which is important and which is still too uncertain. Well, then you go back to the field, so to say, of dedicated experiments, and you change now. Okay, now I need to go here. I need to go to the kinetic rates and study them and design targeted experiments for those. And you do this again, and then you go back with your new formulation for that. You put them in your overall model. You compare to the experiments. You iterate here, and then there is a global iteration, as you see here in green, combining these two. So this is the way we see on modeling and experiments. So you have a model, and then you can have targeted experiments to try to describe, to understand a certain term in your model formulation. And then you have large scale experiments or log data that are used to validate the whole model, so to say. So yeah, you have two kinds of experiments, or we like to see it as you have two different kinds of experiments. Targeted experiments, well, I just wanted to give some examples. Yeah, when you are doing experiments like we did here on the reactivity of char in a fluidized bed, of course, you're not doing experiments in a large-scale boiler, but you do them with the conditions very specific to study, very specific what you want to study with the very specific equipment and setup to study a certain phenomena. And from that, you learn something about that very certain phenomena, and then you feed it into the big model, so to say. And yeah, these are different examples that we have had of targeted experiments. And finally, I would like to end with yeah, a bit of an example, solids lateral dispersion. These we have studied this a lot, and we got funding for this within indirect gasification. And indirect gasification, that is one of the many applications of fluid ice bed technology. But of course, the exciting thing is that the results we get from this, they are relevant for a lot of things, for combustion, for direct gasification, for pyrolysis. The solids mixing is relevant for calcium looping, for thermochemical energy storage, and so on. So what I mean here is that when you study something, again, you're studying it for your application, and that's where you get your funding from typically. But you should always communicate with people with completely different applications, maybe, but still the same technology, fluidization, and try to learn from them, try to collaborate with them, because the main question, how solids mix in this case, but there are many more questions. In this case, how solids mix, that's common to you all. So just because they have another application, don't discard collaboration. The ground mechanism, the underlying physics are the very same, and you should be able to collaborate and learn from each other. Yeah, so I'll be back as I promised to revisit these main statements. All models are wrong and some are useful. So people on this side doing DNS, they claim that they are not wrong. Well, they are still using some to a very low extent, but still some empirical input. And they say that they are true. No, all along this scale, the formulation is somewhere wrong. But the question is what is useful, and there is no general answer for that. Depending on what you do, it will be useful to be on this end of the scale. Depending on what you do, if you're studying a very specific phenomena in a in a very specific region of your unit, then it might be useful to do this kind of modeling. If you are studying boilers as a whole large scale, then it might be reasonable to place yourself here in the middle somewhere. So the question is, what is useful for what you want to do? What is your modeling for? Who will gonna use it? And that, if you answer that question, then you will be able to place yourself in the useful location of this scale, so to say. Theorists and experimentalists should date each other more, and here I've shown that there are here interactions between experiments and theoretical hypotheses, theoretical formulations, models on this level, but also on this global level. And they feed each other. I mean, the models become better if you have the dedicated experiments, the technologies for that can give you insight in your very specific phenomena that you're looking to describe in your model. So here, modelers take help of experimentalists, but here experimentalists take help of the modelers, because with a model you can identify, okay, where is the research need? What is worth doing research on, experimental research on. And finally, the last claim was to better solve your problem, make it everybody's problem. And an example was this lateral dispersion of solids. If we had been alone in this, it would have been a very tough fight. But luckily, we have talked to people and realized together that we are in this together, that we have the same problem, that they are doing combustion, they are doing chemical looping, they are doing other things. We do gasification for this funding here, but the question is the same. So let us collaborate, let us use your setups. You could use our measurement techniques, exchanging PhD students and so on. So it's important then always to see what is the underlying question. Is there anyone else who has the same question as mine, regardless of the application? Yes, so this has been my first lecture here today, and this was the lecture index. And again, I try to illustrate it here that it's important to keep a good balance between proofs and equations. So thank you for that. And let's see. No. There was. I just wanted to bring you another example. We have here that, yeah, how you can develop then the solids lateral dispersion. For example, we have this. We've made it in 2D cold, and this is just a 2D unit, cold conditions, you have a phosphorescent tracer that you track, and this is the very first actions on investigating the mixing of a particle. Then you can go to 3D, still cold conditions. You have seen this video before, and then you can improve a bit more your knowledge, because you are going from 2D to 3D, which is more realistic, but still it's cold conditions. The air viscosity is not the same, for example. So you can get statistics from this. You have improved your knowledge a bit more, your empirical knowledge a bit more. Then we developed a hot probe, a hot camera probe. So this is hot conditions, and we can make digital image analysis on these fuel particles that you see here to try to understand the mixing. And then finally, what we developed was a 3D downscaled method device to try to get full insight. So not only on the surface of the bed, as you see here, but also inside the bed, how a fuel particle will mix. So this is like, I think it's a kind of chronological history or story of how we have been developing in the study of this phenomenon of the solids mixing. So starting from 2D to 3D cold to 3D hot, and then overcoming these limitations in 3D hot that we only can see the surface with new techniques, new technologies that allow us to have insight and track the particle continuously. And now I'm done. So